to thank the organizer and thank Shandong, thank Professor Sandmark, and the distinguished colleagues. And I would like to come here for the first biannual conference for European and Chinese Society of Integrate of Structure. And we would like to, I have worked in this field for 40 years. And we also teaching structural mechanics, teaching different branch of mechanics, compute mechanics, but we find the problem of durability of aging airplanes and don't even the ones have a great challenge for self survive. And this is how we can do with young people. So the engineering. So the engineering from the 1850 as the technology revolution, we review the tri-class made of metal material. We find and so this is usually describe our primitive. We work, we run, and we get tired with fatigue. But we find signs that 150 years ago, we find that maturity also can be into Professor Heskins. I know.
Не, за Михайло все так.
I'll just show it again. It's going to trigger again. Yes, just a second.
You see, the technology provide us the convenience, but also may make things complicated. Now I would like to talk about the three-dimensional fatigue and fracture and the how from fundamental to application. And first, we show the fracture mechanics zero from two-dimensional to three-dimensional. And we know our material have strength and also the toughness. There's a balance between the strength and the deformation ability. We need to refine the crystalline strengthening technology like this one, and also the solution strengthening and atomic level, and intergranule strengthening and also the second phase refinement, especially at high temperature. And all these strengthening have made the material have a local plastic damage accumulation, even at very low strain, especially on the cyclic fatigue loading. And so this is on the cyclic loading, we have the SN curve that find by Wanlin line. This is for 150 years ago. they have a test technology. This is a string, and this is a life. And with increasing fatigue cycle, the bearing string is decreased. And we believe here is fatigue limit, but now the modern technology shows that not this fatigue limit. And so we also find that the crack, the defect is always there, as Shandong have shown us last evening. And so the Griffith criterion bands the energy release rate for the brittle material fracture, and also the William, the linear zero solution for the crack problem. And also we find the Owen have proposed string intensity factor conception that is make it easy to apply the fracture mechanics to engineering problem. We also find in engineering structure is a way toughness and plastic is always occur at the correct type. So in the later 1960s, and Jim Rice, Hutchison, and Riskin developed HR solution. This is the use of J integrate, replace the string intensity factor to dominate the plastic crack type field. So we have completely the two-dimensional fracture zero from linear to plastic material. And so we have a fracture criterion, and also based on this theory and criterion, we have material test that this sets the foundation for our engineering application. And from the Wheeler's age to 1940, before the Second War, there are a lot of airplane design use the self-life principle based on fatigue zero, but they find the safe life is not safe. So we crank and these kind of things occur. And in the 1930s, based on the fracture mechanics zero, we have developed durability and damage tolerant design paragraph. That is based on slow fatigue crack grain and residual strain for defected and corrected body, and not only for airplane, but also for engine. That have signed this year have been the requirement for airplane and engine design. But as we see, all this zero is based on two-dimensional one. And our structure are we three-dimensional, especially when the crack initiation age is always the micro three-dimensional one. So how to use this two-dimensional zero and this two-dimensional zero-based material test property to make prediction for the real structure, three-dimensional structure. The zero is difficult to obtain. And so we till now, not only engine, but also the airplane from Boeing, the airplane, even the China new company, we based on the multi-layer test based material. This is a one layer and analysis, the complete based on test. So this is not economy, and this is the situation. Even though we have Sorry. This is a recent 10 years. The aircraft can crash in the air. The engine fly can like this, or will occur, and even lose the power and induce the crash.
为啥张子枫一直在笑？
The
突然不
rocket
明白。不知道，我看了呀，我就觉得没啥意思，我觉得。哎呀，看我好激励啊！想赶快把台湾打了。爱国主义教育电影。这为啥他演员一直在笑啊？他哥他爸他朋友全牺牲了，他还能笑得出来哦，感觉像个圣人。
hard work, but the real situation is still not smooth one. Why? What's the reason? The three-dimensional one, and so we have a microclamp to break it and to defect all the ring boundary, all the surface manufactured defect, like this one. We have a curve, a frontier of the craft. And along the lower ply of front curve, we have a thin ply. We have a this thin ply element. And this is should be a ply string. Okay, if there is no the normal string along the Z ply in this direction, we call it out of ply string concentration. And this ply concentration, we can use the nominalize this one. This is out of string and over the sum of implied main string. And this is for plus string is 0. And for plus string, and the minimum, maximum is about 0.5. And in a tightly string, through the simply correct front is like this one. It's three-dimensional distribution there. So we have a least limited of this value, and also use a single structure analysis. We reduce the differential equation into a single one. This can be solved like a entire solution. So we obtained the TZ solution. This is you see the TZ is not only dominating the angular distribution, but also during at this term. And here you see. And we also developed in, you see, this is the plus string, this is the plus string, and this is the TZ0, and this is the TZ is 0.5. You see the implicit factor is changed so remarkable. And also the angular distribution. We see this is a denial, but my wrong has least denial, so they have a difference there. We take an example about the parallel creeping solid for three-dimensional crack. We also have this similar equation, and we see here the difference and also the angular distribution, and this is the so the denial I count is tempted. You see, this is a different stream, and this is equivalent stream. And all these curves from ply stream to ply stream, you see the change is so significant. So the three-dimensional effect, the TZ effect, is very, very important. And we have explicit formulation for JTZ for the fraction mechanics, and also the C star TZ solution for treating solid here. So everyone can use it without complicated and methodology for engineering application. So we see, for example, this is through the synchronic crack in a power low treating tensile basement. And this is a finite element result. And the line, this is plus train, this is plus tree. And this is our three-dimensional solution. You see, for this crack and different synchronies, and also we have a different age, and also for the surface cracks with the different angle. This is different angle, and also the corner crack, even down to the nanoscale. And this is about tens of nanometer thin plaque with a crack there. And when we loading this, the micro plasticity occur, and they load like this way. And this is thickness, and this is the toughness. You see the toughness depends on the thickness even below the 10 nanometer in thick. So it's generally one. And too much deny. So I avoid so maybe we deny even in the table. So we have developed the two-dimensional, the linear plastic dripping solid into the three-dimensional one with the KTZ and JTZ and CTZ. We also have high order solution for this kind of zero. And this is a very simple out of line string question in there. Or we apply a very important. And this, and we show here, this is a simply defined KC critical, and this GC the changer with the thickness you see about 3 times. But use this example, it's very simple, concise TZ, like this way, we have the stable and the thickness indefinite value of material toughness in both linear and plastic deformation solid. And for fatigue, we already have a cyclical fatigue and at least the minimum and maximum strain, but the strain range effective for fatigue crack range only the part of crack open junction. So we have to calculate the efficient open part of the decay like this way. It depends on three-dimensional constraint factor that it depends on the thickness and also depend on the TZ distribution. And this is a material, aluminum alloy, with different thickness, different ratio, and collect single lever with this consideration, this high efficient cut. And also for especially very surprised to find that on the crucial environment for given material, given crucial environment, all the curve and collect again to a single beautiful digit EFS curve for different kind of material, different environmental, corrosion environmental, it all is like this. This is a very typical material curve, and this is higher, and this is nearly parallel, and this is lower, is separated anchor relightly track grain in the curve. We can have this as the material balance and corrosion environment. And also very, very crucial one is in our real the Y structure subjected to this random cycle. And so it's a way changer to pass each cycle effective rate for track grain. And we from the 1930s, we have a imperial formula like a Wheeler and a Wheeler charm and this kind of thing. And in the later last century, they developed the owner, the friend, and the US, the NASA have developed the two-dimensional imperial content factor dating or modified strip heading model. And we have extended this zero, use the three-dimensional strip heading model and use the concise three-dimensional string state and free from imperial pyramid to calculate the correct grain on spatial loading one circle by circle. And we can find this experiment is a red data, and this blue line is our prediction for different loading lever. This is on the spatial aircraft spatial loading, and this is on the, you see the different thickness we can make exactly right prediction. So accurately right is impossible. And with this ability, we have largely validated against more than 100 material and loading spectral data. And this one, at least our three-dimensional one, this color, and this red one is the NASA result, and the blue one is the range, the ordinary model. You see, we can make prediction within 2 times of experiment for different material, different spectrum. So with this ability, we extended from throw clamp because material then we use this throw clamp, but the surface and the embodying and the corner and all these three-dimensional clamp was there in real structure. So we have you propose equivalent thickness criterion. Use this one, the same TZ distribution along each point of the curved crack, and the same with the thin through the synchronic crack, the middle ply, we call this synchronic is equivalent. So this there have this one. So we can extended apply through the synchronic data to predicate 1 point by 1 point with different equivalent synchrony. We can make prediction of the three-dimensional crack ring and their shape evolution. And so this we have the initial defect or initial crack. And this is the green without detectable. So this is durability or crack initiation usually. So this is always there. We can make prediction not only the micro crack ring, but also below the detectable side to this initial side. So we have initial, we can examine material, we can have initial quality, and we can do the prediction of durability of three-dimensional growth for the whole line. So the damage tolerant design that should be have wide enough detectable region there from detectable crack is away millimeter micro and up. So that is hard to occur in this kind of critical fatigue structure. So this is a very, very, very small surface. We have polymerization with detailed advanced technology, but in until first microscope, you can see this picture. So this is the initial crack. This is the ascent curve. You see if the initial crack or defect from 10 micro to 15 micro to 500 micro, the knife or the ascent curve have moving so remarkable. So it must consider the quality of surface. This is a typical structure like this one, and correct the we initiated here. This is in air, this is in the caution fatigue on literally. And this data is experimental one. The line is our prediction. So we have ability to make prediction for the durability. And we call this is a ascent curve best fatigue zero, and there are changes about fatigue limit. And we also have a crack green zero based on fracture mechanics. We also have changes about crack green ratio. This not exceed or we bring on this critical point. So between the fatigue and fracture mechanics, the big gap. This gap is durability. So we have fatigue zero, we have fracture mechanics zero, and we have durability zero. So we have a goal from atomic quantum interaction to molecule dynamics study and concise define the microstructure of a material and to the linear and three-dimensional fatigue mechanics, and to finally to the equivalent and survive environment for the structure integrate. This is we showed fill the gap. And this will show how to do to unify the fatigue, and this is a fraction mechanics database. This is the SN curve of the material. We can use them to analysis the intrinsic defect distribution, and this way we find the equivalent crank size distribution in all the new material, new structure. There, we also add the spatial loading, especially the vibration loading and the voice fatigue, and these loading away or not. We can make a prediction of the loading distribution. And based on this initial equivalent crank and this loading, we can make a prediction of the durable reliability, like this one. We have used this kind of thing in engine, in rocket, in airplane, in our engineering project in China. And now we also for high temperature. And this is a very simple CT specimen, and this is a 10 millimeter zinc. This is a 5 millimeter zinc. Exactly the same loading, the same temperature, the same material. They have the creep fraction line about 1 order in degree. So how to make this kind of predication, and also these are with a microstructure thinking. So we have developed a material test method for very large, you see, and this is the place chain, and this is the place chain, but all the data can't fill all the gaps. Even use the heat facility like this one, a huge test machine. And so when we use the correct type theoretical solution like this bag and this bag to make predication of creeping ratio, the creeping fracture time, and we can do with the material basic data. This can occur the option by standard material test, and without only imperial parameter like the critical distance, or we use to use the correct type field to this kind of thing. We read about this one. And this is we show example. For example, this the TZ without and with agree. And we show this the specimen, the light changer in geometry and in synchrony. And this is our experiment. This is our predication, and also for the surface crack, and this one, and this is our predication ability for all the scroll, the synchrony with scroll or without scroll, the surface and the corner crack, and we make predication within the trip error band in high temperature. And so we finally have closed my talk. Is this in this age we have async fatigue design 0, and in last century, and we have fraction mechanics, and we have danger tolerant design. And here we unify the 0 of 3-dimensional fatigue fracture mechanics to make prediction by combine the fatigue and the fracture data for the durability design. This is one.